We now come to the last lecture of this all-too-brief course on black holes. As you have seen, black holes are fascinating objects that allow us to test physics in extreme environments and hence to extend our understanding of fundamental physics. They are also the end states of some kinds of massive stars, and the supermassive variety seem to be intimately related to the growth of galaxy bulges. But sometimes black holes kind of get bad publicity. People are afraid of them. Will we get sucked into a black hole? Ah! Well, as I've already discussed, black holes are generally quite safe. Only at a close distance is the force very strong. Though there are estimated to be millions of stellar mass black holes in our Milky Way galaxy, our galaxy is really big. It's 100,000 light years across. So the nearest of these stellar mass black holes is probably over 100 light years away. It would need to be within our solar system to have a major effect. Indeed, nearby passage of regular stars poses a bigger threat to disrupting Earth's orbit than a black hole wandering around, aimlessly in the galaxy. But recently, mini black holes have been much in the news as a possible threat to our existence. In particular, rumors have spread that the Large Hadron Collider might produce a miniature black hole that will devour the Earth and its inhabitants. Certainly we wouldn't want that. But perhaps such fears have roots in science fiction starting from the 1970s. For example, in 1973, Larry Niven wrote a short story, The Hole Man, in which a quantum black hole from an alien device on Mars was released, and it actually destroyed Mars. Also, in 1990, David Brin had a book, a novel, Earth, where scientists race to avert destruction of our planet by a mini black hole. And more recently, in 2006, there was the made-for-TV movie, Black Hole, where something went wrong at a particle accelerator lab and a mini black hole formed, eating much of St. Louis. Also, some sort of weird energy monster emerged from the black hole and caused many, many problems. Here's a related cartoon, in fact. Professor Maguire was fast regretting becoming the first man to successfully create a mini black hole in the laboratory. This is great. Again, part of pop culture. You can't escape black holes in pop culture. Well, as I'll explain in this lecture, you are safe. Have no fear. Even if the Large Hadron Collider produces mini black holes, which is not at all certain, they pose absolutely no threat to us, none whatsoever. On the contrary, it would be highly exciting if such black holes were produced. They might imply the existence of other dimensions. Wow. Well, first, let me explain some terminology. Hadrons are particles that consist of more fundamental particles called quarks, bound together by the strong nuclear force. Among the hadrons are mesons, which consist of a quark-antiquark pair, and baryons, which are made of 3 quarks. The most familiar baryons are the protons and neutrons, more generally called nucleons, because this is what the nuclei of atoms consist of. Now, a proton consists of 2 up quarks and a down quark. These are whimsical names given to quantum properties of these quarks. The up quarks each has a charge of 2/3 of a unit. The down quark has a charge of -1/3, so you add those together and you find that the proton has 1 charge unit. The neutron has 2 downs and an up, and so it has no charge. The 2 -1/3 add to the +2/3 to give no charge. And the other quantum properties agree with the properties of protons and neutrons. Now, leptons are the other major kind of particle. They do not consist of quarks. The electron and the neutrino, for example, are leptons. They feel a different kind of a force, known as the weak nuclear force. So what is the Large Hadron Collider, or LHC for short, and why has it been built? Well, it's a giant underground particle accelerator at CERN, the European Organization for Nuclear Research, near Geneva, Switzerland, on the French border. Over 100 countries, including the United States, are participating in this vast project. It's estimated that there are 10,000 scientists and engineers involved. This is big-time science. An aerial view shows this ring, this circular ring, 27 kilometers in circumference. It contains evacuated tubes, and they have supercooled superconducting magnets in them that accelerate protons to 99.9999991% of the speed of light. That's fast, but not quite the speed of light. This is the most powerful particle accelerator humans have ever built. The protons move so fast that they can go around this ring 11,000 times in 1 second. You try doing that in your little car, okay? Here's a photograph of one of these tubes, these vacuum tubes through which particles go, lined with magnetic fields created by superconductors. A schematic of the thing shows that it's pretty complicated. This shows only some of the components, but basically there's this beam of protons going through the magnetic field that accelerates it to very, very high speeds, nearly that of light. You collide these bundles of oppositely going protons that are going through the tube. They can collide in certain places where there are instruments manufactured that can measure the particles that come out as a result of the collisions. You get a spray, a zoo of particles at the places where these oppositely directed beams of protons collide with one another. You can also use lead ions. You can collide them. And again, a zoo of particles is created, and these different instruments measure these particles, detect them, measure their properties, and so on. From that, we can reconstruct what happened and figure out what kinds of particles, in principle, exist in the cosmos. One of the instruments is known as ATLAS. It is gargantuan. You can see near the bottom there a person to show you the relative size of ATLAS. These are gigantic, detectors. And the hope is to create particles that have never been seen before, but which perhaps existed very early in the history of the universe, when the universe was extremely hot and dense compared with today's low-energy world. In a sense, we want to recreate conditions shortly after the Big Bang. Now, a really good, spunky description of the LHC, its instruments, and the science it will be doing is given in the Large Hadron Rap, which you can find on YouTube. It's really wonderful. I encourage you to take a look. Well, perhaps the best known goal of the LHC is to create the so-called Higgs boson, sometimes informally called the God particle. It is thought to be associated with a field, the Higgs field, which ends up giving various particles their different masses. Now, a field is just something in space that has a value associated with every point, such as the temperature in a room. Particles moving through the postulated Higgs field encounter different amounts of resistance, like in water or molasses, and this then translates into different masses for the particles. Another major goal of the LHC is to find some candidates for the so-called dark matter in the universe. This is matter that exists, it exerts a gravitational pull, but we can't see it. We haven't detected it. We really don't know what it is. Yet, in fact, it's a dominant component of our universe. I discuss all this in detail in my large introductory course, Understanding the Universe. But basically, by looking at the spiral galaxies and how they rotate, we conclude that there's extra gravity there, causing them to rotate faster than they would have had there not been this extra gravity. Yet we don't see it in the form of stars or other matter. Similarly, clusters of galaxies have galaxies within them that are moving faster than would have been expected had the only matter that's present been the visible matter. So there's a lot of dark matter, and averaged over the universe, it's something like nearly a quarter of the contents of the universe. And we don't know what it is. By the way, most of the remaining 3/4 is dark energy, and we don't know what that is either. Atoms are a minor constituent of the universe. We're sort of the debris of the universe, the afterthought of creation. Not that you're not important, you're all important, but we are minor constituents of the universe. We know that this dark matter cannot be protons, neutrons, or any normal kind of matter. It is thought to consist of weakly interacting massive particles, WIMPs, left over from the Big Bang. But no such particles have ever been detected in a laboratory, so we want to make them in the LHC. More generally, the LHC is designed to help physicists develop and test theories that unify the fundamental forces and particles of nature. An example of such unification occurred in 1865, when James Clerk Maxwell showed that electricity and magnetism were like two sides of the same coin. I have this t-shirt I love to wear in class from Purely Academic. It says, God said, and here are all these equations, Maxwell's equations, and there was light. Because, folks, it's those four equations that describe, mathematically, at least the wave nature of light. It's a set of electric and magnetic fields working together. Although the unification of the forces of nature is the grand goal of theoretical physics, the most thorny issue right now within this goal is the incredible weakness of gravity compared with the other fundamental forces. Though we think of gravity as being strong because it holds us to the surface of the Earth, in fact, it is very, very weak. The incredible weakness of gravity relative to electromagnetism is vividly displayed using this demo. This tiny little magnet holds up the screw despite the fact that the entire mass of the Earth is gravitationally pulling the screw down. The little magnet is winning the tug of war against the Earth. You know, how can that be? Well, it's because electromagnetic forces are so much stronger than gravity. But matter is usually neutral. And also, matter is generally not magnetic, like the magnet. So there are no large-scale electromagnetic forces. That means that gravity generally dominates over big distances, which is why we tend to think that it is so strong. Moreover, the strong and weak nuclear forces have only a very short range, comparable to the size of protons, so we don't generally notice them. In fact, really nobody I know notices the strong and weak nuclear forces. So again, this is why we think gravity is the king, but it's not. It's such a weak force. One of the most promising recent ideas for explaining the incredible relative weakness of gravity is that there are additional macroscopically large dimensions, not just our familiar 3 dimensions of x, y, and z. Our 3-dimensional universe might be like a brain, short for membrane, floating around in a higher dimensional bulk. Now, if gravity resides mostly in some of these other dimensions, with just a little bit leaking into our 3 familiar dimensions, its true strength in the higher dimensional space might be comparable to that of the other forces in our 3-dimensional space or brain. That's the idea. Now, if true, this might allow the formation of mini black holes in the LHC collisions. And that would provide a test of theories having extra dimensions. The presence or absence of the mini black holes would provide a test of these theories. Why might there be extra dimensions? Well, there's a historical precedent for considering them. In 1919, Theodore Kaluza suggested that there are 4, not 3, spatial dimensions. He then found that electromagnetism, Maxwell's equations basically, naturally comes from general relativity, a theory of gravity. There's a deep connection between the two. Gravity is carried by ripples in 3 spatial dimensions, and electromagnetism might be carried by ripples in a new dimension. That is beautiful. Now, in 1926, Oscar Klein refined this idea. He said, well, we don't see this 4th dimension. So he said the extra dimension might be curled up. Not just a circular bump within the familiar extended dimensions, not like a wart on my skin or something, but a tiny new dimension existing at every point. Everywhere that you look, there's this extra little dimension sitting around. Its size might be possibly comparable to the Planck length, 10 to the minus 33 centimeters, 20 orders of magnitude smaller than a proton. String theory is the modern-day, much more developed version of this idea. The idea is that particles are bundles of energy called strings, roughly a Planck length in size, and they vibrate in many dimensions. Different particles are different vibration patterns of strings, like musical notes. And the vibrations occur in the other dimensions, and for the math of string theory to work, you need at least 10 dimensions, and 11 are now favored. The 3 spatial dimensions, x, y, z, time, a 4th dimension, and either 6 or 7 additional dimensions. Most of them, if not all of them, are very small, so we can't see them. But in fact, some might be big. As an example of a small dimension, consider a sheet of sandpaper seen from far, far above it. It looks 2-dimensional. If you were a bird flying way above it, you'd say, hey, there's a 2-dimensional sheet of paper. But if you swoop down and look at it under a microscope or a magnifying glass, you would see the granularity. You would see this 3rd dimension sticking up at every point. But some of the dimensions could be macroscopically large, with gravity residing partly or perhaps even predominantly in these other dimensions. The LHC can test this hypothesis by seeing whether mini black holes are produced by the proton collisions. Let's explore the rationale behind this conclusion. If gravity resides partly in another dimension, then the 1 over r squared force law of Newton would be incorrect. The 1 over r squared force law of gravity comes about in 3 dimensions in a way similar to the inverse square law of light. If you look at a light bulb from twice the distance, it looks a factor of 4 fainter. At 3 times the distance, it looks a factor of 9 fainter, because the same bundle of rays is going through 4 and then 9 unit areas, and each unit area therefore gets less of the light. If, however, you had, say, a circular pattern like this in 2 dimensions, light spreading out would go through a circumference, and the circumference of a circle is proportional to the radius, so light would have a 1 over r, an inverse distance dependence, not an inverse square dependence. Well, it's the same way with gravity. Normally we think that gravity spreads out in 3 dimensions, giving rise to the inverse square law, but really if it goes out in 2 dimensions, it would be a 1 over r, an inverse linear law. And in fact, if gravity went out only in 1 dimension, its strength wouldn't change at all with distance, because it's not spreading out, as you can see here. So in fact, suppose you have a long big dimension and then a curled up small dimension. Now, close to a point source, gravity lines would be spreading out radially like this, and so bigger and bigger circles would encompass all these lines, but that would mean that the number of lines per unit length on each circle would go down. This would be a 1 over r law, like I just described. But far from the point source, the lines of force, the lines of gravity, are not spreading out. So in this case, it would be like the linear example I just showed you. The law of gravity would be constant with distance. So here's a case where gravity doesn't depend at all on distance on big scales, but it does depend on distance over short scales. And in fact, it becomes stronger than anticipated over short scales. Now, in our solar system, we've done tests that show that our gravity law is not 1 over r cubed, but 1 over r fourth is not yet completely ruled out. There are some experimental tests that show that if it is 1 over r fourth, then the general scale over which such a force law could be visible is less than a few tenths of a millimeter, but it's not yet ruled out. And an even greater dependence on distance, say 1 over r to the 5th, is entirely possible. So gravity could be much stronger over very short distances than what we had thought. Now, if gravity is a 1 over r squared law, as in 3D, it is not strong enough to produce mini black holes when particles are smashed together at high energies in the LHC. There simply isn't enough mass in a sufficiently small volume. However, if gravity feels extra dimensions on small scales, it could be strong enough to form miniature black holes, having 1,000 or 10,000 proton masses. There are 2 factors that contribute to this. First of all, if gravity is stronger on small scales, it's easier to trap a lot of material. Secondly, the theoretically expected Schwarzschild radius would be larger in multiple dimensions, implying that one doesn't need to squeeze the matter to such huge, unachievable densities before forming an event horizon. So the production of mini black holes with the LHC might imply the actual existence of other spatial dimensions. How exciting is that? And in fact, if all goes well, the production rate might be as much as 1 miniature black hole per second, something like 100,000 per day. Well, should we fear these guys? No, they will evaporate rapidly through Hawking radiation. So they would last only about 10 billionths of a billionth of a billionth of a second and wouldn't eat anything at all. But you might say, oh, well, I don't believe Hawking. It's just a theory. Well, yes, but according to that theory, that's probably the only way such black holes could be produced in the LHC. You know, if they get produced, they also get destroyed. It's different aspects of the same theory. Well, then you might say, okay, well, I think all these physicists are wrong. Suppose miniature black holes are somehow created and don't evaporate, right? Legitimate concern. Would we be destroyed? This is serious. There was a lawsuit against the LHC for this reason. miniature black holes, and also hypothetical particles called strangelets that would cause Earth to turn into a bunch of strange quarks. Well, don't worry, fear not. Physicists don't want to destroy the Earth, contrary to what it may seem in some movies and stuff where all these mad scientists are doing dastardly things. We've carefully considered the possibilities. The lawsuits are frivolous. First of all, the strangelets would already have been created by a facility called the Relativistic Heavy Ion Collider, but this was not the case. No strangelets. So now let's consider miniature black holes. These black holes, having 1,000 to 10,000 proton masses, would have a tiny radius, but you need to use a different formula for computing the Schwarzschild radius. It would be tiny, but not as tiny as the standard formula. It would be 10 to the minus 16 centimeters, about 1/1000th of a proton radius. Okay, that's really small. Now, gravity is weak, so you really only have to consider the cross-sectional area of one of these black holes in terms of its interactions with other particles. It's not going to go around sucking things in. It just doesn't have much gravity, okay? So let's consider the cross-sectional area, 10 to the minus 32 square centimeters. The Earth's average density is about 5.4 grams per cubic centimeter. Black holes typically travel 300 kilometers before encountering a proton or a neutron. That black hole probably wouldn't even eat the proton and neutron since the black hole is a factor of 1,000 smaller in radius. It might eat only 0.1% of them. But suppose, to be conservative, it eats all the nucleons that it ever encounters, okay? Well, with each nucleon, it'll gain a mass of just 0.01 to 0.1% per encounter. And the trajectory won't be changed by eating this thing. You're just eating a little snack and you keep on going in the same direction. After about 40 encounters, at most 40 munched nucleons, it leaves Earth, 300 kilometers between encounters, 40 encounters, it's gone. And you find that, in fact, in the calculations, mini black holes should generally not be at rest. When you study the details of the collision process, you find that most of them are moving. Only 1 in 100,000 to 1 in a million have a speed less than the Earth's escape velocity. So most of them should escape after one pass through Earth. At most, 1 per day will remain bound. So if 1 per day are created at rest, it could oscillate through the Earth back and forth. It turns out it takes 42 minutes to do a pass through the Earth, regardless of the path you take. This is an interesting fact. It's called the Gravity Express. You go through in 42 minutes. It's kind of cool because 42 is the answer to the question of life, the universe, and everything, according to Douglas Adams. All right, so 40 encounters per 42 minutes, one crossing time. Roughly 500,000, let's call it 1 million nucleons would be eaten per year by the black hole. Even if you create 1,000 mini black holes in 3 years, that's less than 1 billion nucleons per year being eaten. You figure out how many nucleons there are in the Earth, 3 times 10 to the 51st power. 1 billionth of them is 3 times 10 to the 42nd power. The eating rate is 1 billion per year. So it would take 3 times 10 to the 33 years to eat 1 billionth of the Earth. Well, in 3 billion years or so, the sun is going to become way too bright for us to even exist. By that time, only a minuscule fraction of the Earth will have been eaten. We're off by 24 orders of magnitude in time, 10 to the 24th power, to eat just 1 billionth of the Earth. And this is the pessimistic estimate. We have assumed all nucleons would be eaten by the black hole, but really only 1 in 1,000 would be. Now, even if no mini black holes escape from the Earth, you've got 100,000 per day instead of 1 per day, so that brings the discrepancy down to only 19 orders of magnitude. Even if you allow black holes to grow as they eat, you gain just a few orders of magnitude. You're still off by at least 15 orders of magnitude. Even if you want to lose less than 1 billionth of the mass of the Earth, you're off by 6 orders of magnitude. Even if many more black holes are created than we thought, you still calculate that it would take thousands of billions of years to eat any significant fraction of the Earth. It's just not going to be eaten. Don't worry. Another argument is that extremely energetic cosmic rays exist in the universe. They are rapidly moving charged particles produced by exploding stars, gamma ray bursts, quasars, and other active galaxies. Now, the highest energy cosmic rays have energies much higher than those achievable by the LHC. Collisions with Earth would have produced mini black holes long ago, yet the Earth has not been devoured. Well, you might say, oh, that's because the mini black holes produced by cosmic rays go zipping through the Earth, one pass, and escape. Yeah, that's true, but we see lots of old white dwarfs and neutron stars, very dense stars. The white dwarf has the mass of the sun, size of the Earth, it's very dense. Neutron star has the mass of the sun inside the size of a city. It's incredibly dense. The neutron stars especially are so dense that they will have stopped mini black holes from escaping. Yet we see old neutron stars. They haven't been destroyed. Mini black holes should have eaten them long ago, if they eat at all. But in fact, the neutron stars are still there. So the Earth is not going to get eaten either. Don't worry, be happy. The LHC isn't going to destroy us by making miniature black holes. Now, there's a rumor going around that the LHC was actually initially shut down because it produced a mini black hole that started devouring Western Europe, and they didn't want to produce another one for fear of devouring even more of Europe. On the internet, you can find funny animations of this process. This giant black circular thing, just enveloping everyone. It's hilarious, Instead, the LHC was initially shut down temporarily because some of the superconducting magnets failed in one sector, causing a lot of heat to be released and damaging the systems. They had to fix that. I eagerly anticipate hearing about results from the LHC. It will provide a wealth of information, and I especially hope that miniature black holes will indeed be created. They could provide evidence for other dimensions, as well as for the Hawking evaporation process. Moreover, they will show that black holes exist on all conceivable scales, from supermassive to super tiny. Well, now that I've explained why you should not fear black holes, let me end by briefly mentioning some exciting topics of future black hole research. The detection of gravitational waves from merging black holes should be incredibly exciting, with advanced LIGO and hopefully LISA making these detections. This is a real frontier, a brand new window through which to view the universe. By monitoring the gravitational wave signal in detail, we will also determine whether black holes really are simple, as we think they are, having no real macroscopically visible hair. This could be done, for example, by hearing the gravitational wave sounds of a small black hole merging with a large one. Let's listen. From that signal, you can actually probe space-time around the black hole. How great is that? With radio telescopes spread across many continents, we hope to examine the immediate environment of the supermassive black hole in the center of our Milky Way galaxy. This will allow us to test various specific predictions of general relativity in a strong gravitational field. We wish to also better understand how quasars and their supermassive black holes are able to form so early in the universe, within the first billion years after the Big Bang. Also, how do relativistic jets from quasars, as well as the winds from their accretion disks, affect their growth? And can we gain a better understanding of the connection between supermassive black holes and the galaxy bulges in which they live? The existence of intermediate mass black holes in globular clusters and other locations is also possible, but the evidence is not yet compelling. We want to find better evidence. Yet such black holes could have been the seeds from which supermassive black holes formed. So if we find the intermediate mass ones, we will be one step along the way, we think, to understanding the growth of the supermassive ones. Additional examples of stellar mass black holes will allow us to better constrain what kinds of stars turn into black holes at the end of their lives, and to find more direct evidence of event horizons. We also want to learn more about how they are formed in gamma ray bursts, some types of supernovae, and merging neutron stars. We hope to soon measure more accurately black hole spin and find definitive evidence for frame dragging. It should also be possible to determine whether any black holes spin at a rate faster than the theoretical limit. Many black holes have still not been found, yet they are an important frontier. The energies of the most energetic cosmic rays from space are so high that they could conceivably create mini black holes when they smash into molecules in the Earth's atmosphere. These mini black holes could evaporate and explode, so indeed some astronomers are now searching for atmospheric particle showers that could betray their existence. And if the LHC produces mini black holes that evaporate, studies of their decay should help constrain fundamental theories of the universe. Finally, progress in quantum theories of gravity, such as string theory and the competing theory called quantum loop gravity, should help us understand the nature of the black hole singularity, as well as that of space-time itself. Well, this is it. We have seen in this course that black holes are real and have amazing properties. They are far from being just a figment of the vivid imaginations of theoretical physicists and science fiction writers. Of course, some aspects are still very speculative, such as travel through wormholes to other universes. But observational studies of real black holes, as well as theoretical investigations, allow humans to explore the most extreme limits of physics, ever deepening our understanding of the fundamental laws of nature according to which the universe operates. I hope you've had as much fun learning about black holes as I've had teaching you. Keep enjoying the wonders of the universe, and thank you very much.